after spring break. And when is spring break?
Not next week or the next.
Really?
I don't know.
Yay. Okay. All right. Well, that is interesting because when I was looking through my worksheets to figure out what I wanted to do today, when I looked at last semester, the worksheet that I had that came after the one I did before was a test review, but the test review covered Bode plots, which is there's a whole lot left to do if he has the test on power and transfer functions. So we'll see. It could be done in 2 weeks, but we'll just see what all he puts on the test. And so the front page of this worksheet, this was part of what was originally a test review, which is why it has all of this stuff on here. And so I took out the later stuff from the Bode plots, which we'll look at later. And so this is just kind of helpful formulas that you can hold on to this when it comes time to make your formula sheet. You've got them handy. This is not really something that we had specifically laid out as a chart, but you might find it helpful that if you look at the phase of the impedance, and one of you asked me about this the last session, is like, isn't that just the phase of the impedance? And yes, so the phase of the impedance, which is the phase of the voltage minus the phase of the current, if you take the cosine of that, that gives you the power factor. And if that is 0, then you have a power factor of 1, and the current and the voltage are in phase. If you have purely inductive, then you're going to have a positive phase, and the current lags the voltage. If you have purely capacitive, the phase is negative 90 and the current leads the voltage. And so you just have this chart here to come back and look at things. The thing that's new for today that we haven't done yet is talking about maximum power transfer. And so have y'all gotten to that in class yet? Okay. All right.
We were talking about
Shunt capacitors? All right. Yeah, because he had talked about industrial loads, right. Okay, so so here are some, this, like, as you've seen, this is the one that I like to use, that the complex power is the voltage, the complex voltage times the conjugate of the complex current. I have found that most students prefer to use this formula and this formula, just not what I prefer to use, but and the power factor is the cosine of the angle differences, P average over S, and that's because if you look at, and I'd shown y'all this before, but it may make more sense now that y'all have worked more with power. I like the power triangle. I find it useful. So the power triangle, if you take the real power or average power and the reactive power, then the hypotenuse is the apparent power, and this is the angle, that's the angle of the impedance, and then you can see that the cosine of that angle, which is the power factor, is adjacent over hypotenuse, is P over S. So it's all kind of right there in that triangle. And since we're here and we're talking about shunt capacitors, let's talk about like what you would do if you had what can happen is if you have a certain amount of real power, so this is what's useful, but then if you have a heavy inductive load like that, then this is your apparent power. That's pretty big, and so that's what you have to supply. But if you add a capacitor, you can bring this down, and then your apparent power will be smaller. And so you have like this amount of volt amps reactive before, and then after you add your shunt capacitor, you have this much after. And so the circuit's apparent power gets reduced. The real power stays the same. But we'll do an example of that later. But I like the power triangle because to me it makes sense. All right. So now, and then you have maximum power transfer. So you might remember from circuits 1 that with a purely resistive circuit, you have maximum power when the resistance of the load equals R Thevenin. So if you have a AC circuit, then you have maximum power transfer when the impedance of the load equals the Thevenin impedance, but the conjugate of it. Because what that does is it knocks out the imaginary part. And so that'll give you maximum power transfer. And then the maximum power transfer is 1/8 times the magnitude of the voltage squared over the resistance of the load. And it is just R of the load, because if you have maximum power, then you have made it so that the load is purely real. And then I had not known this formula until I had worked out some problems a much longer way, and the students told me that he had given this formula in class, and this is a nice little shortcut for determining the value of the shunt capacitor. And so the value of the capacitance is going to be, like, if you look at that triangle that I drew, this is Q old, and this is Q new. So if you take Q old minus Q new over omega times the RMS voltage squared, that's the shunt capacitor that you want. And Q equals the power times the tangent of the inverse cosine of the power factor. Well, why would that be? So if you look, so if I take the inverse cosine of the power factor gives me this angle, and so then the tangent of that angle is Q over P, and so P times the tangent of that angle equals Q. So not that you'll have a formula sheet, but all of this just kind of ties it together so you can remember how it works. All right. So what is the relation? This is just review. What is the relations between resistance, reactance, and impedance? We've done that a million times, but we had not when I wrote this last semester. Maybe we haven't done it a million times. Okay, so impedance is Z, resistance is R, and reactance is X. So when you're writing the impedance of something, so if it is 5 minus j omega 2, or just put it all numbers, 5 minus j2, if that is your impedance, then the resistance is 5, and the reactance, which has the symbol X, is minus 2, is the reactance. What's the relationship between real power, reactive power, and apparent power? So which one is which? So I have S, Q, and P, and which is which?
S is apparent power. Q is reactive power. P is
Real power, and what's the other name for it?
average.
Average power. And apparent power, actually S, is actually the magnitude of the complex power. So S in bold or with a little squiggly on it is the complex power. And the complex power is P plus JQ. And the units of power are watts. The units of apparent power are volt amps. Now, volt amps actually have the same base unit as watts. So if you take watts, a watt is a joule per second, and if you break these down, they end up having exactly the same units. This is just a way for us to distinguish between them. They don't really mean anything different. It just lets us know what we're talking about. And then Q is volt amps reactive, VAR. What is the phase difference between the voltage and the current in a resistive circuit? So if I have a resistive circuit, let's say my voltage is 20 angle 0 degrees. Then my current, whatever it is, what's its angle have to be?
0 degrees.
Also has to be 0 degrees. So if I have a reactive circuit, so purely reactive, no resistance, so only capacitors or inductors, then if I had V equals 20 angle 0 degrees, then the angle for I could be one of two things. What could it be?
Plus or minus 90 degrees.
It could be 90 degrees or minus 90 degrees. And which one would be for an inductor and which one would be for a capacitor? So if you look back here, we've got this nice chart. So capacitor would be negative and an inductor would be positive. So power factor. The definition of the power factor is the cosine of the phase angle of the impedance, which is the cosine of the voltage minus the current and so when would that equal 1 and when would it equal 0? So when does cosine equal 1?
Is it still circuit?
So it equals 1 when the impedance angle equals 0, which means it is purely resistive. And it equals 0 when the angle is plus or minus 90 degrees, so purely reactive. Which one do you want if you're trying to be efficient?
Resistive.
Okay. A wound coil that has an inductance of 180 millihenries and a resistance of 35 ohms is connected to a 100 volt 50 hertz power supply. So our frequency is 50 hertz. You can always say with a problem like this, you can say that your voltage is at 0 degrees and then everything is measured from that, because there's not like an absolute zero, it's just relative to each other. So we have the frequency, and we know we have the frequency and not the angular frequency because it's in hertz. And so we need to get the angular frequency, which is 2 pi f. And that would be I don't have that one worked out separately. So I know that, and y'all can check my work on this. So let's see. So the impedance for our inductor is J omega L. So that would be J times 2 pi times 50 times 0.180. And I get that to be 56.55. Anybody have a calculator? We can just believe me. So then our impedance is 35 plus J 56.55. And then let's get that in polar. And in polar, I get that it is 66.5 angle 58.2. So can you tell me already whether current leads or lags voltage? It lags, and there's several ways we know that. We know that because these things all go together. Our angle is between 0 and 90, and it was an inductor, and it's lagging. So the current lags the voltage. So those things all go together. So a positive angle, an inductor, and lagging all goes together. So why was it a kind of a nice idea to go ahead and get this angle right here? How does that help us answer the questions that are coming up?
You can calculate current, it's like easier to do like when you divide phasors.
Oh, sure, that makes sense too. Yeah, that is true. I was thinking of the fact that the power factor is the cosine. This angle is the angle for the voltage minus the current. So I've got that already. And I was just thinking it would be easy to jump ahead to part C because I've got that angle already. So I'll just go ahead and do that. So cosine, but yes, that is true. It will make it easier to do that. So I get a power factor of 0.53. And then our current, I equals V over Z. So I equals 100 angle 0 over 66.5 angle 58.2. Which is 1.5 angle negative 58.2 amps, and my unit for impedance was ohms. Power factor doesn't have any units. And the apparent power consumed, since it says apparent power and not complex power, let's see, could do it just using I feel like there's an easier way, but I'm not coming up with, I always just go back to my old standby, so that's what I'll do. So S equals, now they did not tell us this is RMS. I feel like it is, but this is an RMS kind of number, but it should have said RMS. Without saying RMS, you don't know. And so if it doesn't say RMS and it's a test question, I would say, is it RMS? And then you might get like an answer, like, does it say it's RMS? In which case you'd say no. Okay, but I would just go with, I would ask, because like numbers like 100 and 120, those are like real common numbers for RMS. So I'm going to change my problem and put RMS in there. So with the RMS in there, then I don't need to have a 1/2, and I would say S equals V times I conjugate, or 100 times 1.5 angle positive 58.2. That's my complex power. So that's 150 angle 58.2. But my apparent power is just the magnitude of that. So my apparent power is 150 VA. So, any questions on that? All right. What is power factor correction? Have y'all done any of that yet? We've talked about it a little bit.
Shunt capacitor.
Mm-hmm. Yeah. So, so what do we mean? What do we want to do? What would we do here?
You add elements to the circuit to make the power factor closer to 1.
Yeah. You want to make the power factor closer to 1, because when the power factor is closer to 1, that means that you've got all your real power. And usually what happens, as you know, is that you have too much inductance. And so usually you add a shunt capacitor. And the shunt capacitor will cancel out the effects of the inductance. I'm gonna stop here and save this and start a new one.